Okay, let's say we have a study of greatness here. And we see that David is greater than Donna and Bill is greater than David. We also see that Bob is greater than Dan. Now, what's the first letter of the name of the greatest? Well, think about it. You have Bill is the greatest of these three, and Bob is greater than Dan. The greatest of all is either Bill or Bob, isn't it? So whoever's greatest, you don't know whether it's Bill or Bob, but it's one of them. It's certainly not Donna or David, because they're not as great as Bill, and it's certainly not Dan, who's not as great as Bob. It's either Bill or Bob, and all we need is the first letter of the last name. So there's a fairly obvious solution here. Donna and David aren't. Dan isn't. So it's either Bill or Bob. And the first letter is B. Now, we didn't really use a plan for this one either. We just saw what was going on. But the implicit plan here is elimination. We eliminated the ones that we knew weren't the greatest, and we're left with two candidates for the greatest, and fortunately they both had the same first letter in their name. Had they not had the same first letter, the strategy wouldn't have worked, and we might not have had enough information to solve the problem. Here's another problem. Okay, we want to fill in the blanks, the 4 blanks, so that this addition makes sense. Now, how do we do that? Well, again, we simply first try to understand the problem. You know, that when we add this column, we're going to have to get something that ends in 8. Then when we add this column, it's got to end in 0. And when we add this column, it's going to have to be 14. So how are we going to start? Well, we could start really from either end. If we're going to get 14 here, 8 and 1 is 9, we'd have to have a 5 here, right? And if we get a 5 here, well, wait a minute now. That might not be the case. Let's see. We could carry something from this side, couldn't we? So if we add these 3 numbers up, we're going to end in 0. That means we're automatically going to have a 1 to carry. So I guess what we really need here is a 4, because we'll have carried the 1, and that'll give us the 14. Now, what number are we going to have here? Well, that depends. We're going to have something carried here, aren't we? It's really easier to start from this end. We could start from this end and figure it out, but we're going to have to look over and see what got carried and what didn't. So if we start from here, we're going to see that if 5 and 6 and something add up to something that ends in 8, well, 5 and 6 is already 11. The biggest this could be would be 9, which would give us 20, which means that we're going to have to end up with 18 in this column. So that 5 and 6 and 7 are going to add up to 18. And that's the only number that can go here and give us an 8. 5 and 6 are already too big. So now we're going to have a 1 to carry here. And if we carry a 1, let's see, 1 and 3 is 4 and 4 is 8. This number can't be bigger than 9. So this is going to have to be 10 here, isn't it? So in order to make this 10, this number here is going to have to be 2. So 1, 2, 3, and 4 make up 10, and we got a 1 to carry. Now if there's a 1 to carry, then as we saw in this column, which has to add up to 14, we've already got 9 and 1 is 10. We're going to need a 4 here, which is going to give us a 1 down here. And there's no other way to do this problem. There's no other way to fill these in to make that all true. Let's ask another one. What's the minimum number of pitches that you could throw in a baseball game that lasts 9 innings. Now, you might think about a baseball game. What's the minimum number of pitches you can take to get a batter out? You might think 3 pitches. Well, yeah, if you're going to strike them out. But you can get a batter out in 1 pitch if the batter swings and hits the ball and either grounds out or flies out or whatever. Okay, if the batter's out for one reason or another, then it might only take 1 pitch. So we could see that each batter really needs only 1 pitch. Now you have 3 batters every inning, so if you have a 9-inning game, there are 27 batters if you multiply 3 by 9. So it would seem that each team would have 27 batters, which would be a total of 54 batters. If you get each batter out on 1 pitch, you could get by in 54 pitches. Now that's not quite right. You might ponder what's wrong with that while I write some of this down. Okay? So we could say, okay, plan, well, 3 batters per side per inning, least number of pitches, 1 per batter. And of course, to be out, the batter just about has to hit the ball, and unless you have a really easy pitcher, that's not likely to happen on 1 pitch with every batter, but this is at least possible. Okay, 1 per batter. So 3 per inning. Now there are 9 innings. Which implies 27 batters per side, question mark there, 27 pitches per side, 54 batters. Well, this 27 batters per side isn't really true. Okay, if you have 27 batters on one side and 27 on another, of course your game's going to end up 0-0. You wouldn't have a 9-inning game. It would go into extra innings. So you now have to conclude that, well, somebody has to hit a home run in the first pitch so that one team can win. And if that happens on the team who has the second at bat, then that team's not going to come back to bat in the last inning, right? So you now have to consider all these other possibilities. This really is part of understanding the problem. We're understanding the problem and working out the details at the same time. So maybe our best assumption one home run, everyone else out, 1 pitch each batter, and then you can carry out this plan and think through what's going to happen. Remember that it's possible that the second team won't have to bat in the last inning. So then you can think of how to adjust some of this analysis.